This paper introduces a novel class of generative models based on piecewise deterministic Markov processes, PDMPs, which are non-diffusive stochastic processes consisting of deterministic motion and random jumps at random times. The authors leverage existing literature on time reversals of Markov jump processes to characterize the time reversal of any PDMP, demonstrating that it is also a PDMP with characteristics related to the original PDMP. The authors focus on three specific PDMPs: the Zig-Zag process, Bouncy Particle Sampler, and Randomised Hamiltonian Monte Carlo, and show that the jump rates and kernels of their corresponding time reversals admit explicit expressions depending on some conditional densities of the PDMP under consideration before and after a jump. They propose efficient training procedures to learn these characteristics and methods to approximately simulate the reverse process. The authors also provide bounds in the total variation distance between the data distribution and the resulting distribution of their model in the case where the base distribution is the standard d-dimensional Gaussian distribution. Their contributions include characterizing the time reversal of any PDMP, specifying the characteristics of the time reversal processes associated with the three aforementioned PDMPs, and defining their piecewise deterministic generative models employing either ZZP, BPS, or RHMC as forward process. The author's approach takes advantage of the scalability and reduced computational complexity of PDMPs in high-dimensional settings, making them an attractive alternative to diffusion-based generative models. Their proposed models have the potential to bridge the data distribution to a base distribution, and their time reversal can transform samples from the base distribution into synthetic data from the data distribution. The authors introduce the concept of time reversal for PDMPs, which is crucial in the context of generative modeling. They show that the time reversal of a PDMP with characteristics phi, lambda, q, is a PDMP with reversed deterministic motion and jump rates and kernels satisfying a balance equation. This result is applied to derive the backward jump rate and kernel for the ZZP, BPS, and RHMC, which are necessary for the time reversal of these processes. Here is a combined summary of the 4 pages. The research focuses on time reversal of piecewise deterministic Markov processes, PDMPs, specifically ZZP, BPS, and RHMC, by approximating their characteristics, including jump rates and kernels. For ZZP, the authors introduce a class of functions to estimate density ratios and define an objective function inspired by ratio matching to learn these ratios, which is equivalent to minimizing another objective function that can be optimized without knowledge of the true ratios. For BPS and RHMC, normalizing flows are proposed to model the conditional probability distributions of the velocity given its position at any time, enabling both density estimation and sampling. To approximate the backward refreshment mechanism of a PDMP, the authors minimize the loss function LML theta equals minus ZTF0 dt omega t e log p theta vt xt t, where p theta vt xt t is the conditional density of the forward BPS with respect to the Lebesgue measure. The optimal parameter theta b star operator is estimated by maximum likelihood, and the backward refreshment mechanism is defined accordingly. The authors employ a splitting scheme to approximate the integral in the backward rates lambda t x v equals s theta x v tf minus t lambda x rv, where s theta is an estimate of a density ratio and r is a suitable involution. This scheme approximates the PDMP with a Markov chain defined on a time grid, simulating the deterministic motion and jump part of the PDMP separately. An error bound in total variation distance is derived between the data distribution micro and the law of the synthetic data generated by a PDMP with initial distribution pi circled times nu and approximate characteristics. The bound accounts for 2 sources of error: initializing the backward PDMP from pi circled times nu and estimating the backward rates. Numerical simulations on simple synthetic datasets demonstrate the performance of PDMP-BASED generative models, which are evaluated by the kernel maximum mean discrepancy (MMD), and shown to perform well compared to the improved denoising diffusion probabilistic model (IDDPM). This research introduces novel generative models based on piecewise deterministic Markov processes, PDMPs, focusing on three specific PDMPs from the sampling literature: ZZP, IDDPM, and BPS. These models are implemented using neural networks and compared on various synthetic datasets. The results demonstrate the potential of PDMPs in generating high-quality samples, particularly when using ZZP with a sufficient number of backward steps. Table 2 presents the mean-maximum mean discrepancy, MMD, results for the 2D rows dataset, showing that ZZP outperforms IDDPM and BPS for a large number of backward steps. Figure 1 illustrates the generated data, showcasing ZZP and BPS's ability to produce more detailed edges compared to IDDPM. Figure 2 compares the output of RHMC and IDDPM for a small number of reverse steps, highlighting RHMC's ability to generate data closer to the true distribution. The importance of network architecture in achieving state-of-the-art performance is discussed, and potential directions for future investigation are identified. For instance, separating the estimation of density ratios and generation of velocity draws could be beneficial for BPS and RHMC. Exploring alternative PDMPs and efficient techniques for learning high-dimensional networks are also suggested. The paper's contributions lie in introducing a theoretically sound framework for PDMP-based generative models, providing a comprehensive comparison of their performance, and identifying areas for future research. The results demonstrate the potential of PDMPs in generating high-quality samples. Furthermore, the research delves into various aspects of stochastic processes, diffusion models, and their applications in machine learning, including time reversal of Markov processes, piecewise deterministic Markov processes, and their connections to statistical inference and optimization techniques. The significance of these concepts and their relevance in modern machine learning and artificial intelligence research are highlighted. The paper constructs a non-homogeneous piecewise deterministic Markov process, PDMP, with multiple jump types, characterized by its characteristics, phi, lambda, q, where lambda and q are time and state dependent, and phi governs the deterministic flow between jumps. The extended generator of the PDMP is given by equation 11, incorporating both deterministic and stochastic components. To establish the validity of the PDMP, the authors prove proposition 1, which requires verifying technical conditions, including the integrability of the jump rate lambda and the existence of a compactly supported function space F, dense in the domain of the extended generator. Under the paper's assumptions, F is equivalent to the space of twice continuously differentiable and compactly supported functions, C2_C, E. Furthermore, the authors prove proposition 2, which involves the flux equation for a PDMP with position-velocity decomposition in a homogeneous jump kernel. This proposition is crucial for establishing the time reversibility of the PDMP, essential for the paper's main results. The proof involves manipulating the flux equation to account for the position-velocity decomposition and the homogeneity of the jump kernel. The paper then discusses the time reversals of ZZP, BPS, and RHMC. For ZZP and BPS, the time reversal has a vector field given by phi-1, x, v, equals, v, 0, t. The jump rates and kernels are determined using the conditional law of the velocity vector given the position vector at time t, with initial distribution mu_0 circled times nu and invariant distribution pi circled times nu. The authors assume that H4 holds and that R mu_dx _I psi x less than infinity for all I equals 1, d, and E mu_nabla psi x less than infinity for BPS. These assumptions enable the application of proposition 2 to each pair, lambda_I, q_I, and verification of the proposition's conditions. In both cases, the key to the time reversal is the application of proposition 2, providing a general framework for computing the backward jump rates and kernels for PDMPs. The resulting backward jump rates and kernels are used to define the time reversal of the PDMPs. The research discusses the application of splitting schemes for discretizing time-reversed piecewise deterministic Markov processes, PDMPs. It focuses on the RHMC, ZZP, and BPS algorithms, detailing their pseudocodes and highlighting differences and similarities. The RHMC algorithm initializes from a given distribution or a proposal distribution, iterating through updates and proposals. The ZZP and BPS algorithms follow a similar structure, differing in velocity flip handling and density ratio use. The paper also explores the convergence properties of these algorithms, specifically the H2 norm, and provides a proof for Theorem 1, bounding the difference between the initial and evolved distributions in the TV distance. This involves introducing an intermediate PDMP with the same characteristics but different initial conditions, leveraging the triangle inequality for the TV distance. The study relies on assumptions from the uniform distribution on the sphere and the d-dimensional Gaussian distribution, verifying general conditions and utilizing deterministic jumps and refreshments. It connects to previous works on non-explosiveness and density ratio matching, demonstrating the technical depth and precision required for this field. The research paper explores the application of data processing inequality to bound the total variation distance between two probability distributions, introducing Markov semigroups and utilizing the coupling inequality for bounding the TV distance between two PDMPs. Focusing on the ZZP, the authors aim to bound the function GT defined in equation 8, and detailed their experimental setup, which includes the use of neural networks for ZZP and IDDPM, and neural spline flows for RHMC and BPS. The experiments are conducted on a Cascade Lake Intel Xeon 5218-16 cores, with varying durations depending on the dataset and sampler. A comparative study of different probabilistic models for generating images is presented, focusing on backward PDMPs and their splitting schemes. The authors compare the performance of three processes BPS, RHMC, and ZZP with the IDDPM model in terms of accuracy and efficiency. In Table 3, the mean 2 Wasserstein distance, W2, for different refreshment rates is presented, averaged over 10 runs, indicating that the ZZP process outperforms other models at higher refreshment rates. Table 4 shows the mean W2 for different time horizons, demonstrating that increasing the time horizon generally improves the quality of generated data but may require longer computation times. Experiments on generating handwritten digits using the MNIST dataset are also included, where the ZZP process is trained with a U-net architecture, employing an exponential moving average and self-attention blocks. The results in Figure 4 show promising outcomes, indicating the potential of the ZZP process in generating realistic images. The authors use PyTorch for all experiments and emphasize the importance of choosing appropriate hyperparameters and architectures for each process to achieve optimal results. The study highlights the trade-off between computation time and data quality, as well as the need for careful tuning of refreshment rates and time horizons. The results suggest that the ZZP process could be particularly useful for applications where high-quality images are required and computational resources are limited. The research paper discusses the development of a novel generative model, ZZP, trained on MNIST, focusing on its capabilities in generating complex patterns. The ZZP model leverages advanced mathematical concepts, such as stochastic processes and optimization techniques, to produce high-quality digit images. The paper highlights the significance of these results, emphasizing the model's potential in various applications, including data augmentation and image synthesis.